Hello, everyone. Welcome to lecture 32 of AREC 333. Today, we will continue with risk and production. For today, we will first do a right-hand side risk analysis. We will use a method called chance constraint programming. And I will also show you in Excel how you can do this risk analysis. This is linked to the EV analysis example that we covered last lecture. And after that, if we have time, I will introduce another method that you can use for analyzing risk in production, which is called decision tree. You probably have already heard of this method from other contexts, but what I'm hoping that I can show you in this course is giving you a risk in production problem, then how you can use that verbal problem to draw a decision tree, and after that do the decision tree analysis. There's two approaches that you can use to do a decision tree analysis. Here I listed the CE approach and the expected utility approach. CE is certainty equivalent, and expected utility is also linked to CE. And I hope those two concepts are not new to you, because we did spend quite some time covering what's expected utility and what is CE in previous lectures. So for readings, the Hadker et al. 2004, chapter 2 and 6, those are for the decision tree analysis, and Kim et al. Chapter 8 and 9 are for the risk analysis part. So here you can pay particular attention to 9.3.2, which is specifically about the right-hand side risk. So first, in last lecture, what we did was actually the objective coefficient risk. So we mentioned in last lecture that they, let me see, I probably have the problem here. Okay, so in last lecture, this was the problem. And remember, we said if the decision maker or the producer is uncertain about the expected profit, then the decision maker can maximize what we call it E minus 5V, and this V is the variance, and that's a measure of the risk. So if there's uncertainty about the objective function coefficient, then we can do the EV analysis like what we did in the last lecture, and we can also generate the EV frontier. And that's how we deal with objective function coefficient risk. What if there's right-hand side risk? And we did this in the linear programming problems. So there's three types of parameters in the mathematical programming problem. And we have objective function coefficients, we have right-hand side values, we also have technical coefficients. If those sounds unfamiliar, you should go back to the farm management linear programming problems, and we did cover there what are each of those three types of parameters. So here we are again focusing on the right-hand side parameters. So usually the right-hand side parameters are the resources available to the decision maker, for example, the land available, or here I give another example is the availability of field time. That depends on weather, so that's one type of the right-hand side risk. And I did mention in detail why is that a risk. So for example, if the fields are too wet for the equipment, then such as plowing, disking, planting, harvesting, and so on. So those can be completed. So if there are uncertainties on the right-hand side value, then that might also affect the producer's decision making. And we can do analysis using this method called CCP, which we call it chance constraint programming. And let me first introduce to you here the mathematical writings of this programming methods. And then following these mathematical equations, I will also use an example, which is the EV analysis example we have been using in last lecture. So first is there's this constraint with a stochastic right-hand side. And if there's risk there, then we can write it this way. So on this part, everything in black, that was the Euro constraints that we have been seeing. This AJ1, AJ2, and AJ3, those are the technical coefficients. And the X1, X2, and X3 are the decision variables. So you can imagine X1, X2, and X3 here are the acres that the producer allocated to grow wheat, soybean, and corn. So those are X1, X2, and X3. And AJ1, AJ2, and AJ3, you can imagine that as for each unit of X1, so for each acre of the land allocated to wheat, then what is the requirement for maybe labor? If if on the right, if this constraint is about labor, then that coefficient should be related to the labor use. And on the right-hand side, this BJ here should be the, let's use labor, for example, then that's the amount of labor available. For example, it could be 1,000 hours or 5 days and so on. The reason that I use this J here is because for each mathematical programming, we could have multiple constraints. So for example, we could have constraint on land, constraint on labor, constraint on field time, and so on. So for each of those constraints, that's one J. So J, you can say J equal to 1, then this is land, J equal to 2, then it's labor, and so on. So if that J is bothering you, then you can just forget about it. So this could be just A1, A2, and A3, and you get that, get rid of that J. And if you drop the J, then that is one particular constraint. So that's the general explanation of this constraint here. What is really different is this minus Z alpha and sigma J here. So let me first explain to you what's sigma J. So BJ here is the mean of the resource available. So when there's no risk, we know for sure, for example, there's 1,500 of labor hours available. However, if there's uncertainty, then here we can calculate the mean of the resource available, and the sigma J will be the standard deviation of the resource available. And we did cover in previous lectures how you can calculate the sigma. Sigma is the square root of your variance, or you can say variance is sigma square, and that's a measure of risk. And then once you calculate the square of sigma, you can take a square root and get the standard deviation. So alpha is a statistical term that is the significance level if you have to take statistics course. And this alpha is a predetermined value of the probability. And that means it is you or the decision maker who decide this alpha level. So usually this alpha will be, for example, 5% or 10% or 1%. And what this alpha mean is that it means that the probability of this constraint met, it is greater or equal to 1 minus alpha. For example, if alpha is 5%, then 1 minus alpha is 95%. And then you will say there's at least 95% chance that this constraint will met. Or you can say I'm at least 95% confident that this constraint will be met. And Z alpha is actually the score, and it depends on the alpha value that you choose. And it's called the critical value, and the alpha is derived from alpha, so that a lower value than this Z alpha will have a chance of occurring 1 minus alpha % of the time. And it might be a little bit abstract of describing it this way. I think if you have already took a statistics course, then this might be very easy for you to understand, but don't worry if you don't, and let me explain to you what is this Z alpha here. First, again, is the normal distribution PDF here. And we know in the middle it's mu, and then to the left is 1 sigma, and to the right is also 1 sigma. So those are the mean and the standard deviation. So, and we also explained what that mean is, that within to the left and to the right of 1 sigma, within this range, then there's 68.2% of the chance that here, if on the horizontal axis it's your profit, then it's your profit located within that range is 68.2% of the chance. And let's assume that it's a normal distribution for whatever the interested variable you're looking at. Then Z-score means, so this is a standard normal distribution. That means its mean is 0 and its standard deviation is 1. And here, this alpha is equal to 0.05. Again, that's what we choose. So we can choose alpha equal to 1% or 5% or 10% or whatever the other values that you prefer. And once you choose that alpha value, it means that that region, the probability of those shaded region there is actually 5%. And then to the right of that vertical line, the probability of that value, assume this is X, it could be the profit. So X, the probability of X is greater than whatever that value there is. We will mention what that is. Then it's 1 minus alpha, because to the left is 5%, and then to the right it will be 1 minus alpha. So then your Z value is Z alpha. It's called the critical value. It is, for the standard normal, is this number, minus 1.645. And you can see here, it is minus 1, and here is minus 2. So if it's not a standard normal distribution, this will be 1 sigma, 2 sigma, and this will be 1.645 sigma, and there's negative signs in front of those values. So that 1.645, negative 1.645 is the value here, where to the left, the probability of your X value is to the left of that Z alpha is 5%. So if we want to choose a different alpha value, for example, 10%, let's say it's here, then the region to the left of that value, that's 10%, alpha equals to 10% or equal to 0.1. Then this value here will be z 0.1 or z 10%. So the z alpha here is just to the left of that value, then the probability happening is alpha. So that's the alpha value and the z alpha value. So what you should do is first decide your alpha value, how confident you want it to be. You want to be 95% confident, then alpha will be 1 minus 95%. And if you want to be 99% confident that that constraint is going to be met, then your alpha will be 1 minus 99%, which is 0.01. And once you decided your alpha value, then you can find this the alpha value. For different distributions, there could be different z alpha value associated, but in this course, we will only focus on normal distribution. So once you decide your alpha value, then your z alpha value is also decided. And also, I should mention here, if you have studied a statistics course, this situation here is called the left-tailed test. And if you have two-sided test, and then if your alpha is still 5%, then each of those shaded regions should be 2.5%. That's when you are having a two-sided test. And in this course, we're not interested in that. In the course, we're only interested in this left-tailed test. So you don't need to worry about that. But just in case you're confused, that's the difference there. So let's actually work on an example here. So here I also provided you guys a table of the critical values. So once you decided your alpha value, then you can calculate what's 1 minus alpha, and you can find your z alpha value. So what you usually do this is that there's a table of critical values in any statistics course for a normal distribution. And once you decided your alpha value, then you can go to that table and try to find your z alpha value. But in this course, I just provided the several z alpha values that you might need, so that you can save the trip of trying to get that table and find the values there. But if you're interested, you can practice and try to say if the values I provided here are the same as what you found from the critical value tables. So again, here in this course, usually if there's an assignment question or if there's an exam question, I will just tell you the alpha value. It could be any of those three numbers. And once you find that alpha value, then you should come back here and find the alpha value. I will not tell you directly what's the alpha. So you do need to find the alpha value here. So this table could be important. And let's actually work on the examples. So for example, this is the labor availability of the EV analysis example that we used in last course, in last lecture. So this was the EV analysis example, and we do have this constraint here that the higher labor is smaller or equal to 1,000 here. So this 1,000 is the BJ. And The S, W, and C are the X1, X2, and X3. And then the 1, 1.1, 1.3, those two are the AJ1, AJ2, AJ3. So that's that constraint. And last time, or in last lecture, we know for sure that there's 1,000 hours of labor available. However, now, suppose there's risk there or there's uncertainty here, so that the labor available is not certain. So from past experience or past observation, the farmer or the producer find that the labor availability for the past 5 weeks are 600, 800, 1,000, 1,200 and 1,400 of hours. So it's not for sure 1,000. And if there's uncertainty here, then we can take this into account in the decision making. And we need to use this CCP method here. So this, because here this uncertainty is about the labor availability, so it is the right-hand side risk. And remember that for the right-hand risk, we mentioned here that we need to do this to make a little bit modification of the constraints. We need to minus this Z alpha times sigma j, and now the Bj is the mean of the resource available. So we come back to the problem. We need to find out our Bj, which is the mean. We need to find Z alpha and sigma j. So here, the Bj should be easy to find. It's just the mean of those 5 values, and that should be 1/5 times 600 plus 800 plus 1,000. And so if you do the calculation here, you will find it equals to 1,000 here. So the mean labor available, this is the labor here, is 1,000. And once we find out the mean, we can also calculate the standard deviation here. So I did cover in previous lectures how can you calculate this sigma or the standard deviation, but let me do this again here. So to calculate the standard deviation, we need to calculate the variance, because the variance is the square of standard deviation. So the variance, if you still remember, it is the expectation of x squared minus the expectation of x, and then take a square of that whole expectation. And this Ex, what's inside that bracket, we have just calculated. That's 1,000, and it's this B labor there. And what we're left is try to find this X squared. So let's do this. In this example, we assume that there's equal probability of each of those 5 availabilities there. So this will be 1/5 times 600 square plus 800 square plus 1,000 square plus 1,200 square plus 1,400 square, and then minus 1,000 square. So that's the definition of the variance. And then you can do the calculation here. I'm not gonna go into details, but I will do the calculations really quick, and you should practice this yourself. And this is equal to 36 plus 64 plus 100 plus 114 plus 196. And then I'm gonna minus 500 here. And if I do this, it will be 8 times 100 square. So that's the variance. And if you want to know the standard deviation, that's the square root of the variance, 800 square, and that will be 100 times square root of 8. And if you get the value for square root of 8, then it should be that number 283 or 282 points, I don't remember, 8 or 9. So that's how you calculate the standard deviation. So we get the B, we get the sigma, and we left with the Z alpha here. So this is the risk neutral person's problem. And if there's a risk here, then we need to make changes to that constraint and replace B with B labor minus Z alpha times sigma labor. And this is 1,000. And this sigma labor, we just calculated this 283. And then we will need to decide the Z alpha value. And what's the Z alpha value? So usually, as I mentioned, that's what you or the decision maker should decide. Let's assume that we want to be confident for 95%. And then we go back here. Our alpha value will be 5%, and 1 minus alpha will be 95%. Again, here, once you choose alpha equals to 0.5, then 1 minus alpha is 0.95, and that means there's 95% of the chance that this constraint is gonna met, or it actually should be this constraint. So you are 95% sure that that constraint is gonna met. And once you decided the alpha value and you calculated 1 minus alpha, then you can find in this table that the Z alpha is 1.645. And then you go back here, replace that Z alpha with the exact number that you find there. So once you make changes to your constraint, then you can use Excel and then solve the problem again. And what you can also do is try with different alpha values and then see how your results change. So let me actually show you this in Excel, and probably it's more clear there. That's how you can calculate the BJ, the sigma, and also the Z value, the alpha values there. Okay, so here is the CCP Excel template for the right-hand side risk. And in this Excel, there are several tabs here, and the data, which were the profits for the 3 activities. And we also calculated the mean here, and also the variance covariance table. And this is all we have been covered in last lecture. We also have the risk neutral persons linear programming problem here. We also have the quadratic programming. That is what we covered in last lecture. And this is a tab for when you record your results if you choose different expected profit level. And you can record your optimal solutions here. You can also calculate your phi level here, and then after you do all that, you generate this EV frontier graph. And that's all covered in last lecture. So in this lecture, this is a CCP tab, and that is the chance constraint programming. So it is still very similar to this QP risk neutral problem there. So the only difference is this cell. So this resource endowment here, you need to make changes to that cell. And since this is a risk analysis, and we mentioned that if there's right-hand side risk, we will need different Z alpha values. So I just put this Z alpha value here in case I need it. So this is again from the table provided in the slides. There are 3 Z alpha values, and this 1.645 here is corresponding to 5%, alpha equals to 5%. And then in the example, we're given that the labor, there's 5 possibilities of labor availability. And we can calculate the mean. And here you can see I just use the formula, which is average of those 5 cells there. So you can calculate that. And this is a standard deviation. You can calculate this number by hand, just like what I have showed you in the slide, and then provide this number here. So we said it was 283 in the slides. However, there's also an Excel formula that you can use to calculate the standard deviation here. So this on the outside is a square root function, and inside that is a covariance function. And we mentioned that variance is just a special type of covariance. So that's when the 2 arguments here are the same, then your covariance is just your variance. And you take a square root of your variance, you got your standard deviation. So again, I'm not asking you guys to do this. If you're interested, you can maybe spend a little bit time on this formula here. However, if you are not interested, it's totally fine that you calculate this number by hand and then just input 283 here. So we have everything ready here. Now what we need to do is, again, as I mentioned here, you need to change this cell. This is a hired labor constraint, the right-hand side value of that constraint. And here, this E18, as you can see, this is a blue cell. Here is the mean, so this is a B labor. And then this A20 is the Z alpha value. So here we choose this number. This is 1 alpha equal to 1%, and 1 minus alpha equal to 99%. And this CCP F18, the purple cell here, is the standard deviation. So this formula here is exactly the same in the slide in the formula in the slide. So once you provided that formula here, then you can solve this problem. So this problem is already solved for this Z alpha value. Let's actually change this number to 5 alpha equal to 5%. So now it's here, alpha equal to 5%, and you can notice here that this right-hand side value changed. And now we can solve this problem. Solver, and here again we can use a simplex LP because this problem is linear programming problem again. And then you can also click solve, and okay, our problem gets solved. So you can see the profit here is different, and here we also have the decision variables there. And what you can do is that you can resolve this problem by choosing different Z alpha values. I just show you guys when the alpha is this number. Let me actually also show you when you choose alpha equal to 10%, and this is a Z alpha value corresponding to alpha equal to 10%. So what you need to do first here is change this Z alpha here. Oh, I think I did it wrong for the Z alpha equal to 1.65. So excuse me about that. So here is the Z alpha value. That's okay. However, here it should be the sigma value here. So this is right. So your B minus your Z alpha times your standard deviation. Let's actually solve this problem again. Sorry about that. So, okay, again, this is Z alpha equal to 2.326, and that is corresponding to alpha equal to 1%. So we solve this problem, and that's the solution here. And let's actually solve this problem for Z alpha equal to 1.282, and this is alpha equal to 10%. And let's solve this problem. Solve it. And you can notice here this corn, it changed. The max expected profit also changed. And last, let's also solve this problem for Z alpha equal to 1.645 here, and click enter, and I solve it again. And again, you can notice here the solution changed. The maximized expected profit also changed. So after each time you solve your problem, you can keep a record of the optimal solutions here and also the objective function value here. If you're interested, you can also keep a record of the resource endowments here, or the labor availability there. So that's how you can solve this problem in Excel. And again, you can record your results for different alpha values and then put them in a table. So if you keep a record of your solutions and the labor availability and also the profit, which is the objective function value, then you can get this table. So let me explain to you here first. Is you find your alpha value, then you can calculate your 1 minus alpha. And once you calculate that, then you can use the table provided in this course or any other the critical value table for normal distribution, then you will be able to get your Z alpha value. And for different Z alpha values, we showed in Excel how you can calculate the right-hand side value corresponding to those different Z alpha values. And those are the three right-hand side value for the labor constraint. And then those three columns here are the optimal solutions for each of the Z alpha values. And again, the last column here is the profit, or the expected profit, which is the objective function value here. So once you put everything together, then you can kind of take a look at the results here. So again, once you choose your alpha value, then this 1 minus alpha here means that how confident you are that the labor constraint can be met given there's uncertainties in the labor availability. So if you want to be 99% sure that the labor constraints can be met, then this is, this is the corn that you want to allocate. This is the land that you want to allocate to grow corn, and you don't want to allocate any land to soybean or wheat. And the profit you can get is this much. However, if you relax your confidence level a little bit, for example, this time you say, oh, I don't need to be 99% sure, I'm okay with 95% sure, then you will grow a little bit of corn and your profit got higher. And if you want to be even a little bit of riskier, you say that I want to be 90% sure that the labor availability will be met, then you will end up growing more corn and your profit will be higher. So what you can get from this result is that this chance constraint model it discounts the resource available. So here, as you can see. So if you want to be more certain, so here 99% certain that the constraint will be met, then the discount is the largest. And if you want to be less certain, the discount will be moderate. So that is the impact of the right-hand side risk of the farmers' decision making here. So we only covered this one example for the right-hand side risk. And again, in this course, we are not covering the risk on the technical coefficients. However, if you're interested in Kim et al., there was examples there. So feel free to read those sections, and I believe there's also examples there and how you can do it in Excel. So with that, we finished the right-hand side risk part of the risk production section. And I do want to mention that there's advantages of CCP and there's also limitations here. So in general, as I have shown you, the CCP method is fairly simple to use. Once you decided your Z alpha value, then you can do a linear programming problem. All you need to change is the right-hand side value, depending on the Z alpha value that you choose. So the data requirement is also simple, and you only need past observations of the resource available, and then based on that data, you can calculate the mean, you can calculate the standard deviations. Sorry, here it should be standard deviation of the right-hand side, and that's all you need, and you can do your CCP analysis. However, there's also limitations here, and first is if you choose your right-hand side value and you solve your problem. In the example, this didn't happen. However, it could be possible that what if the recommended solution is not feasible? So you solve the problem, it gives you the solutions. However, for example, if the solution asks you to plant 1,000 acres of corn, however, you only have 500 acres of corn, that could be possible under CCP. And if that happened, then CCP didn't tell you what to do. And also, I assume, again, the decision process is static. It's not dynamic or here sequential. And I do want to touch a little bit on the production and time, but not too much because we will need advanced techniques to do that. But I will probably spend half lecture to at least get you guys exposed to the problems when time is relevant when you're making production decisions. However, with that, that's all I want to cover for the mathematical programming for risk and production. There's another section, another approach that you can also use to analyze risk and production, which is a decision tree approach that I mentioned at the beginning of the lecture. We will not be able to finish the decision tree analysis today, but let me get started. So first is an explanation of what is a decision tree. So a decision tree is what you're seeing on the right side here. Here it's a horizontal tree. However, if you rotate it to the left of 90 degrees, then it is kind of a tree shape. So it's a map of possible outcomes of a series of related choices. And it started with a single node. So this is a node here. It's also a node here. It's also a node there. So those are nodes. And then after it started, it branches into possible outcomes. So starting here, there's two possible outcomes there. And then each of those outcomes will lead to additional nodes. And if there's more process, it could also branches further on. So that's different branches. And then, as I mentioned, if you rotate it to the left, it's a tree-like shape. And let me also explain to you the names of the nodes and the branches of this decision tree. So first is the decision node. So this is a square here. So pay attention to the different shapes in this decision tree. So here it's a square. That means that's the decision node. That also means that at that node, the producer or the decision maker should make a decision. And after that, that decision node branches to two other nodes here. Those are circles, and that's the chance node. So the circles are the chance nodes, and that's showing the multiple uncertain outcomes. Let me first give you the names, and then I will give you an example. And the tree, there could be other processes in between, and then at the end, so those triangulars there are the endpoint nodes. That means that's the final outcome. So once you see this, there's no more branches. After that, that's the end of that particular branch. So there's three different nodes here. Square means a decision need to be made. A circle, you don't need to make decision. It means there's chances. And once you say a triangular, then that means it's a end node. So we also have names for the branches. So if you say there's two branches there, or it could be three, then those are called alternative branches. So here it's also alternative branches. And when you're doing your decision tree analysis, sometimes you realize that, for example, here, this branch is not favored and you want to reject that alternative, then you put two slashes there, and that means it's a rejected alternative. And later on, we will show you when you should put that slashes there. And finally is what we call it in decision tree analysis fork. So there's two different types of forks here. First is a decision fork. It includes the decision nodes and also the branches there. And also there's also a event fork. So this is different from the decision fork is because at the beginning it's a chance node. It's not a decision node. And again, this chance node together with branches come out from it. Together, it's the event fork. And I do have an example here of a foot and mouth disease (FMD) outbreak, and a dairy farmer is worried about this risk, and depending on whether there's an outbreak or not, or the decision maker has to make a decision whether to buy an insurance. So if it buy an insurance, then it will get some certain payments. And if it didn't buy the insurance, then it will depend. If there's no outbreak, then it gets some payment. And if there's outbreak, there's also different scenarios depending on whether the infection found on that particular dairy farm's farm. Then the the losses are also different. So we will leave this to the next lecture where I will show you how you can draw a decision tree for this problem and how you can attach numbers to the different nodes of that decision tree. And after that, how should this dairy farmer make the decision when it is facing the risk of a FMD outbreak.